3.4, Zeros of Polynomial Functions. The first thing we need to discuss if we're going to go through an algebra course is the fundamental theorem of algebra. The fundamental theorem of algebra says you know that an nth degree polynomial can have at most n zeros. In the complex number system, this statement can be improved. And so what this says is if you have a third degree polynomial, you could have at most 3 zeros. What's a third degree polynomial? An x cubed function. And again, this is at most not guaranteed. That is, in the complex number system, every nth degree polynomial has precisely n zeros. And so if we're talking about complex numbers, that is a for sure statement. But this important result is derived from the fundamental theorem of algebra, and let's look at that. So the fundamental theorem of algebra states, if your function is a polynomial of degree n and n is greater than 0, then f has at least 1 0 in the complex number system. So using this fundamental theorem of algebra and the equivalence of zeros and factors, we get the following theorem. If we have a polynomial of n degree, then it has precise n linear factors. So note that this fundamental theorem of algebra and the linear factorization theorem tell you only that the zeros or factors exist, not how to find them. So it's kind of a summation of what all we've come to up to this point. We get this theorem to be true. So what we're going to do is we're going to look at it and we're going to say, you know what, if you had like a first degree polynomial such as f of x equal to x minus 2, it has 1 0. It's a 1 degree polynomial. It has at most 1 zeros. And so if you were to set this equal to 0, you would get x to be 2. If you have a second degree polynomial, see second degree, you could have at most 2 zeros. Well, in the case of this specific one, you factor it out, you set it equal to 0, you draw your table, and you have a 0 at 3 and 3. So they can also be a repeated 0. Note in this one, we have a third degree polynomial, so see it's x cubed. So you factor this out and you get x times x squared plus 4. X squared plus 4, you can go ahead and factor that out and you get x plus or minus 2i. And the way you get that is, if you look at this, say you stopped here and you had x times x squared plus 4. You'd say, okay, let me look at this. Let's let x equal 0. And let's let x squared plus 4 equal 0. Well, this one's already solved. That's that answer. This one, you get x squared equal to negative 4, when you move it over. And then when you square root it, you get x equal to plus or minus. Well, the square root of 4 is 2, but since there's a negative in here, we have to put an I with it. Remember that 1.5 section? And so this is how they're able to get it factored into minus 2i and plus 2i. But again, if you would have stopped here, you could have seen that you would also get the same answers. So it's a third degree polynomial, and this one actually has exactly 3 zeros. Bringing us to one of the big concepts for Chapter 3 and probably the harder questions on your exam to come, the rational zero test. The rational zero test relates the possible amount of zeros to the leading coefficient and to the constant term. So whereas the fundamental of algebra tells you how many you might have, the rational zero test actually says, hey, let's find them out. And so what you do is, considering your polynomial, and we've written this several times, there's my polynomial. You look at your lead term and your back term, and you look at those coefficients. And you do p over q. So this will be your p, and this will be your q. P is the factor of the constant term, and q is a factor of the leading coefficient. So let's do some examples and look at that. So to use the rational zero test, you first look at the list of all rational numbers whose numerators are factors of constant term and whose numerators are factors of leading coefficient. Okay, that sounded crazy. So let's look at this. You form this list and use trial and error to figure it out. So what does this all even mean? Let's work with real numbers and see what it means. So to find the rational zeros, here's what you do. This will be your p and this will be your q. And again, it's the coefficients. And so if I put p over q, then I'm putting negative 6 over 1, and I'm going to look at the factors, meaning what to multiply to give me this. So in order to do this, you do p over q, and you think, what are factors of 6? Well, 1 and 6, and I'm going to consider positive and negative. 2 works, so 2 and 3. And if you kind of make it in this order, you can notice there's no numbers between 2 and 3, so that's my whole list. Over what are the factors of 1? What to multiply to give you 1? Positive and negative 1. Then you divide each of these. You say 1 over 1, 2 over 1, 3 over 1, 6 over 1, which doesn't change anything, but it gives you a list of plus or minus 1, 2, 3, and 6. So because the leading coefficient's 1, the possible rational zeros are factors of the constant term. That just happened out. But by applying synthetic division successfully, you can determine that x is equal to -1 and x is 2 are the only rational things. So you look at all your options, and all of our options in that last one are 1, 2, 3, and 6. And I'm going to do lots of examples, so don't get scared right now. So what you do is you try one. So we're going to try -1. Remember, that's one of these options here. You line up your coefficients. We got this coefficients from our equation, and then you do synthetic. So you bring it down, you multiply, add, multiply, add, multiply, add, multiply, add. You get 0 as a remainder. So it says, yep, that's a 0. Then from your answer, we're going to take these coefficients and do it again. I'm going to try 2 because notice that's in my list. I do synthetic on that. It gives me 1. Multiply, add as you go. You get 0 as a remainder. So this shows that x equals 2 is a 0. So to figure this out, we can say, you know what? So what are the factors of this problem? X plus 1, that's that x equals -1. X minus 2, that's that x equals 2. And then I have this as a remainder. I started as a 4th degree, so I got a 3rd degree. I started a 3rd degree, so I get a 2nd degree. So I get x squared plus 3 as my remaining. So the rational zero test tells you possibilities for zeros. You use the possibilities in synthetic to break it down and to end up with your factors and also a list of what the zeros are for this problem. So you can see in this, because the factor x squared plus 3 produces no real zeros, meaning if I set x squared plus 3 equal to 0, I get x to be positive negatives square root of 3i, which I can't graph an I on this graph. Then you conclude that -1 and 2 are the only real zeros. So -1 and 2 are the only real zeros of s, which is verified with this graph. Now note, synthetic division can be used to test the possible rational zeros. Finding the first zero is often the most difficult part. But after that, the search is simplified by working the lower degree polynomial, working with your answer from synthetic, as we did in that one. So x equals a would be your 0, and x equals a is also called a solution. All this being said, we're going to talk about conjugate pairs. So I'm trying to save our examples till the end so that we can kind of use all this together and go slowly. So we have to talk about conjugate pairs because the pairs of complex numbers always complex numbers always comes in pairs. So if you have a plus bi, you're guaranteed to have the conjugate negative. And that we've already learned and tested over conjugates. So let f of x be a polynomial function that has real coefficients. If a plus bi is there, then also a minus bi is there. So be sure that you see that this result is true only if the polynomial has real coefficients. So if we want to find a 4th degree polynomial, and it has real zeros at -1, -1, and 3i, we have to go up. 3i always has a partner, so we also need -3i in there. And so we would say, you know what, I'm going to have a positive 1, that's our negatives up here. And I'm going to have a 3i and a -3i. And so this would be all my factors. And then I can multiply this thing back together in order to find out what that polynomial function is. You multiply this thing back together, and you get x squared plus 2x plus 1, that's your x plus 1's being multiplied back together. And then your x minus 3i and x plus 3i when multiplied back together give you the x squared plus 9. Multiply it all and you get this 4th degree polynomial. So when you're working with multiplying the zeros back together, then you want to do the imaginary ones together first and then put them with the real ones, because you can see that since they're conjugate pairs, I'm not going to end up with any imaginary piece in there. So we're going to look at factoring a polynomial, and I'm going to look at a lot of examples and kind of walk through this with you so that you're able to handle this more proficiently. And this is probably the hardest stuff, I would say, for this chapter. Okay? So let's do some examples. Okay, so here's what I want to do. What if I'm given f of x equal to 2x cubed plus 3x squared minus 8x plus 3? And I want to factor that, or I want to find all the zeros of that. Then what you're going to do is you're going to first do your rational zero test. Now the rational zero test says that you need to put p over q. So if I'm doing p over q, that means I'm looking at 3 over 2, and I'm looking at their factors. What will multiply to give me 3? Well, that's only 1 and 3. What will multiply to give me 2? 1 and 2. you're going to do 1 over 1, so I have positive 1, positive negative 1, and 3 over 1, so I have positive negative 3. And then you're going to do 1 over 2, so you do all your possibilities, 1/2, and 3 over 2. So 3/2. So that means this has degree 3. So at most I could have 3 zeros, and they're going to be hiding in here. Not all of them are going to be hiding in there because these are only the real ones. But some of them, we have a way of jump starting. So what you do is you try one. So let me try a negative 1. If I want to try negative 1, I put negative 1 out front, and then I take my coefficients from my polynomial and I do synthetic. So I bring down the 2. 2 times negative 1 is negative 2. Then you add 3 minus 2, 1. Negative 1 and 1 give me negative 1. Add, multiply, add. Now when you get to this point, you go, oh, I didn't get a 0 there. If your remainder is not 0, then that means negative 2 was not a 0. So you try again. You say, okay, let me try positive 1. I told you the most difficult step is getting the first one. If you're not very good with synthetic, I would ask you to go back and review synthetic, get a good handle on that before you start putting it with this. Bring down the 2, multiply, add, multiply, add, multiply, add. That gives me a remainder of 0. So this says, yes, 1 is a 0 of the function. So I could say x minus 1, and then this is a 3rd degree, so that means this is a squared, times 2x squared plus 5x minus 3. That thing right there is equal to what we started with. Now I got to keep breaking it down some more. Now you can do your rational zero test and work it with that quadratic, but since we know how to work with quadratics, or we should, I'm just going to go ahead and factor this. So that'll be a 2x and an x. My signs are going to be different, so let's say minus 1 plus 3. You can set all that equal to 0, and you get your zeros to be 1. And I'm just setting 2x minus 1 equals 0 and going from there. So that would give me x to be 1, 1/2, and negative 3. So my rational zero test gave me possibilities. I tried some possibilities till I got one, and then I kept breaking it down from there. So if this problem asked me to find zeros or solutions, here they are. If it asked me to fully factor it, here it is. And we couldn't have gotten here without the help of that rational zero test. Let's try again. So this one comes from your book. Let's see. It says, take f of x equal to x5 plus 2x. Nope. Okay, so x5 plus x cubed plus 2x squared minus 12x plus 8. And it says write as a product of linear factors. So we want to write it out as the factors. And list all the zeros. So that's my 2 goals. So I'm going to take this function and I'm going to first do my rational zero test to see what my possibilities are. So remember, you put p over q, so I'm looking at the factors of 8 over 1. I got my p here and my q from that one that would be there. Factors of 8 are 1 and 8, 2 and 4, all over 1. So if I divide all those out, I'm really just looking at 1, 2, 4, and 8, the positive and negatives of them. Then you just trial and error to try and find it. So I'm going to try negative 1 to start with. I would start with my 1s, unless you have a hankering for what you think it might be. So you put in your coefficients. And remember, you have to put in 0 for any term that's missing, otherwise it'll throw off your whole problem. And you multiply, add as you go. And that gave me 20. So that's not 0. Then you try another one. Let me try 1. And sometimes you might have a hankering like, you know, that looked like it was about to cancel out, but really it didn't because it should have subtracted instead of added. And so then you can try, you know, the opposite of that. And so I do my synthetic, bring it down, multiply, add as you go. Ooh, I messed up. Oh, I missed a term. That's fine. Okay. That was a 1 and 2, not a 12, excuse me. So multiply, add, multiply, add, multiply, add, multiply, add. So be careful with your writing. Sorry, that was a 1 and a 2, not a 12. So since that was my remainder, and it was 0, this says that this is a 0 of this function. So look at that. I already got one of my zeros. Once I find 1, this shows me that I have x minus 1 times, this was an x to the 5th, so this will be an x to the 4th, x4 plus x cubed plus 2x squared plus 4x minus 8. And then I need to keep going from there. So I try another 0. I'm not going to go back and try -1. You could. It might work out. But probably not. I'm going to go on to the next screen. And so let me try -2. Now when I go to try -2, I'm working with what I had left, which was 1, 1, 2, 4, -8, not from the beginning. So I'm going to do synthetic as I go. And again, I get a remainder of 0. Yep, that's a 0 too. So now I'm looking at x minus 1, which I already had, x minus 2, and then this was an x to the 4th, so that means my answer is going to be 1 degree lower, so I'm going to have x cubed minus x squared plus 4x minus 4. Now once you've done it a couple times, especially the 5th degree like this, sometimes it's good to reevaluate and say, okay, what are my p's and q's, just looking at this thing. Well, that would be 4 over 1, so I'm looking at 1, 2, and 4 all over 1, so just these factors, because when you divide them by 1, that's what they are. And so I'm going to try again, and I'm going to try 1, because you could have a repeated 1. And I'm going to use 1, -1, 4, -4 for my coefficient, so I bring it down, multiply, add as you go, and I get a remainder of 0. So now I have x minus 1, x plus 2. This x minus 1 that I just grabbed, and if this was an x cubed, that's an x squared, so x squared plus 4. And I can work with that. If I factor out this x squared plus 4, that's an x plus 2i and an x minus 2i. And get all my other factors written in red here. So they asked for the fully factored form. There's the factored form. What are all my zeros? Well, my zeros would be 1, -2, 1, but I'm not going to list it twice, and then positive and -2i. So if you're asked to work a problem and they want you to find the zeros or they want you to find the factors, just kind of take your time, go in order, use your rational zero test to find the possibilities, and then use those possibilities to give you a jumping point in order to factor or solve this zero out. If you need any extra assistance, let me know. Use WebAssign, use the homework help in the modules, all this stuff to help you out.